So, good morning, everyone. Thanks for coming in great numbers. Actually, it's relatively full. This is nice. So today, it's my pleasure to well, not present. You know her. Most of you know Banafsheh. She will give the seminar talk today. So Banafsheh Shahzamanian is from Iran originally, although she's German now, as you can see. And she got her astrophysics, she got a degree in physics and a master in astrophysics in Iran, and then went to Cologne University in Germany, where she got her PhD in a framework of the Max Planck Institute Research School that they have there. She got her doctorate degree with Andreas Eckert, working on polarization, infrared polarization studies of the Galactic Centre. After that, she got a grant for 2 years from the Bonn-Cologne Graduate School to stay as a postdoc in Cologne. And then, fortunately, she came here. She chose to come here and work in our ERC project. And now she is actually financed from the Severo Ochoa program as a postdoc to work in the Galactic Centre project. And she's doing something really new now, some unprecedented study of proper motions in the Galactic Centre. And that's about all I have to say. And now Banafsheh will tell you about her work.
Okay, thank you very much, Rainer. First of all, hello everyone. Today I want to talk about large-scale proper motion study of the Galactic Centre. I will start talking briefly about Galactic Centre, or GC. We'll show you the data set that we use for our work and the analysis that we did on the data. This is an infrared X-ray image of the Galactic Centre. The brightest region in this image is the position of the supermassive black hole, Sagittarius A star. We have 3 known clusters in the Galactic Centre: Arches cluster, quintuplet cluster, and nuclear star cluster, which is around the position of the Sag A star. If we zoom in this nuclear star cluster, you can see the zoom-in region, which is a multi-band near-infrared image that shows the position of Sag A star, the black hole, and the stars around it. So Galactic Centre is located 8 kiloparsec from Earth, and it is the closest galactic nucleus to us, and it is where we can resolve individual stars on the scale of milliparsec. Okay, this is the structure of the Galactic Centre. The solar system is located in the galactic plane. The galactic disk is outlined here with 2 black lines. We have here the galactic bulge, which in the middle has the nuclear bulge here. And nuclear bulge consists of nuclear stellar disk and nuclear stellar cluster. These patches here that you see, these black patches, are the position of a spiral arm of the galaxy. We have the compact giant molecular clouds in the line of sight to the GC, and that's why we have the extinction. So Galactic Centre is a unique laboratory or template for galactic nuclei and for extreme astrophysical conditions and environments. It has the highest stellar density in the galaxy. It has a warm and turbulent interstellar medium, and it has a high magnetic field. It is unique in its observational difficulties because its observation suffers from extreme interstellar extinction, and that's why we cannot observe Galactic Centre in optical. It's totally dark. And in our work, we observed it in near infrared. And another problem to observe Galactic Centre is the source crowding. And to resolve this problem, we have to use the highest possible angular resolution. So in Galactic Centre, we have active star formation happening. And there are different evidences that show that this star formation is active. One of them is the presence of massive and young clusters, the 3 clusters that I showed you before, with a mass of 10 to the 4 solar masses and age of 2 to 7 mega-year-old. And the other evidence is the stellar disk structure called nuclear stellar disk that is located here, and I showed you before, with a radius of 200 parsec, and it emits 10% of total galaxy Lyman continuum, but it only occupies less than 1% of the whole galaxy. And another evidence is that recently 3 classical Cepheid have been discovered in the position 30 parsec to the position of Sagittarius A star with a star formation of 0.08 solar mass per year in the past 30 mega years. So all these evidences show that Galactic Centre is the most active galactic star forming region in our galaxy. So the existence of at least 10 or more undiscovered young clusters is expected in our galaxy. But we cannot easily detect these young clusters in the Galactic Centre. And the problem is due to the extinction. The extinction is quite high and is very variable toward the GC. And that's why we cannot use the normal investigation of color magnitude diagram because these diagrams are reddened and they cannot be used to identify young clusters, at least in the GC. And there is another problem that the projected densities of these young clusters drop below the background density after only few mega years, so we cannot resolve them. So the answer to these difficulties is using stellar proper motions. Stellar proper motions are powerful and alternative way in order to detect these young stellar clusters in the GC. So in order to start our study, we have a pilot study for our large-scale proper motion of the GC. We started by using 2 high angular resolution survey, Galactic Nucleus survey and HST Passion Alpha. The time baseline between these 2 epochs is 7 years. Now I will introduce each of these surveys that we use for calculating proper motions. So the first one is Galactic Nucleus, is a near-infrared JHK imaging survey of nuclear bulge. The PI of this survey is Rainer, and it is based on an ESO large program of 160 hours of observation. And the data has been reduced by Paco, which was a former student of Rainer, was here, and he also produced a catalog for this survey. And the observation has been done on Hawkeye at VLT. So I just want briefly to introduce what is Hawkeye. Hawkeye is a near-infrared wide field imager. You can see the field of view of it, how it is. It has 4 different detectors that we call them chip 1, 2, 3, 4. And you see that there is a gap between these 4 chips. And the field of view on the sky is around 7.5 times 7.5 arc minutes. So this image shows all the galactic nucleus regions that are overplotted on a Spitzer image. So the background image is a Spitzer image, and on top of it, the galactic nucleus regions are overplotted. This direction is the direction of nuclear stellar disk with all the regions on top, and this is the regions that are used for comparison, and they are in the inner bulge. And you can see here again the position of Sagittarius A star, the position of other clusters that I talked about, these 3 famous clusters. So galactic nucleus is high angular resolution. It has 0.2 arcsecond resolution with the help of a speckle holography technique. You can see here a mosaic of this survey here in this image. And for doing a speckle holography, one needs short integration exposures in the time of observation, and that's why the field of view of Hawkeye has been reduced to 1/3 of the whole field of view in order to have short exposures to do a spectral holography. And if we compare, if you see this image of galactic nucleus with the next slide, which is from another survey for infrared Galactic Centre observation, which is called VVV, you see a huge difference between the resolution and the angular resolution of VVV. This survey is around 0.7 arcsecond. And this plot shows that we can reach 2 magnitudes deeper with using galactic nucleus in K-band compared to using the VVV. So we can go much deeper and we can resolve much more stars by using galactic nucleus. And so far, it is the most complete and deepest survey for Galactic Centre observations available. And the catalog has 3.3 million stars, and it is in the area of 6,000 square parsec in the sky. So here you see a final RGB using JHK image of galactic nucleus survey. I mean, here you don't see much good resolution of it, but it's quite nice, and we can resolve very good clusters and a lot of stars around. And the region that we were interested and we started our analysis with is pointing 19, which has 6 arcminute distance from the position of Sagittarius star. It's shown here with F19. So we have a lot of fields to study, but our pilot study is from this field. And we concentrated, and as I showed you, the Hawkeye is divided to 4 chips, and we concentrated on chip 1. And here you see the zoom-in image of chip 1. And we started with this field because we realized there are some H2 regions located in this region. And H2 regions are interesting because they can be the indicator of presence of young stars. So for doing our proper motion study from JHK, we just use the H-band data of this survey. Another survey, the second survey we use for our proper motion is the HST Passion Alpha survey, which is at NICMOS with NIC3 camera at HST, and it has a 1.9 micrometer wavelength, and this is high angular resolution also, 0.2 arcsecond, and the PI of it is Wang, and also Dong did, that was a former postdoc of Rainer. He did basically most of the work on this survey. So here you see the final mosaic of this HST Passion Alpha survey, is this image here. That is for the central region of the Galactic Centre. And you can see how it is just for this region. So now you see in this image that we have a small field of view of NICMOS shown in this yellow square here. So we have the mosaic of Passion Alpha and we have the mosaic of NICMOS, but we didn't use that for the purpose of proper motion. And we just used the small field of view of NICMOS because it could give us more accurate compared to using the whole mosaic. So for this reason, we have, for instance, in this small chip of Hawkeye, we have 8 images of HST Passion Alpha to calculate the proper motion. And here you see the zoom-in image. And this is, if you see this bow shock shape, this is a H2 region, one of the H2 regions in the whole region. And there are different H2 regions in the Galactic Centre. This is one of them that is called H1, H2 region. And it was basically discovered and studied in radio and other infrared works before. And as I said, it's very interesting because it can show the presence of young stars. So in order to calculate the proper motions by having these two epochs, one at 2008, the other one at 2015, we should be able to obtain proper motions. But we have two epochs from two different surveys, so we should transfer them in the same reference frame. So we transfer our position of stars from NICMOS on the reference frame of Hawkeye by rotating the position and also to correct the pixel scale of the images, and also to do the alignment procedure. This alignment procedure is done by the third degree polynomial, and it's quite tricky because it's very sensitive. The field of view of HST, as I said, is very small, is 50 arcsecond by 50 arcsecond. So when you want to transfer these images on top of Hawkeye images, the small field of view can produce a lot of error in the alignment. So one has to be very cautious to do this kind of analysis. So we get the proper motions, and also we obtain the uncertainty of the proper motions. The uncertainty consists of three different steps. One of them is the astrometric uncertainty of Galactic Nucleus survey, which is around 1 milliarcsecond for bright stars. Here you see the uncertainty versus magnitude, that is around 1 milliarcsecond for just bright stars. And also is around 2 or 3 milliarcsecond for the other survey, HST Passion Alpha survey. And another uncertainty is the alignment uncertainty, which is around 1 to 2 milliarcsecond. And here you can see the interpolation map of alignment uncertainty that shows how this uncertainty changes versus the position on the image. And it is unfortunately worse when we reach the edges of the images. So finally, we can have the proper motion uncertainty versus the H-band magnitude for this field of study, this pilot study F19 chip 1. And we continued to get the velocity distribution for our proper motions in two directions, in the direction parallel to the galactic plane, Vx, and Vy perpendicular to the direction of the galactic plane. And we obtain velocity dispersion for these velocities, and we cannot say it is intrinsic velocity dispersion because it is folded with the proper motion uncertainties, so it's not really intrinsic. So in order to check, so till now we obtain proper motion and uncertainties, but in order to check if we are really doing things correct or not, and in order to check the feasibility of our method, we calculated the proper motion for quintuplet cluster, and we compared our results with the result of the previous works. Here you can see the quintuplet cluster at Hawkeye, and the right-hand side image is the same cluster with NICMOS. So we obtain proper motion, and this is the uncertainty of the proper motion versus H-band magnitude. There's a difference between this plot and the same plot for the other field that we studied, and this is due to the fact that quintuplet cluster is full of very bright stars, and that's why the distribution of uncertainties is different. So this plot shows, it's called vector point diagram of proper motion, and it is has been calculated for the quintuplet cluster. So what it shows, in the x-axis you see Vx, which is the velocity parallel to the galactic plane. On the y-axis you see Vy, which is the velocity of stars perpendicular to the direction of the galactic plane. The dashed line here is the direction of the galactic plane. So this kind of plots are usually used to see where is the cluster population. And here you see close to the origin, we have our cluster population that moves along the direction of the galactic plane. Here you see also the histogram of it, which peaks here, the cluster population, and it is followed by a distribution of field stars that we have. And we have also the distribution, the histogram on the V direction. So we compare this vector point diagram with the works of other people, previous works, and we see that our result is consistent with previous works. So the difference is that here the north and east is different, but is the same distribution. So this is the direction of galactic plane, and this is, for instance, in this figure, this is the direction. We have the cluster population, we have the field star population. Here the same, the cluster population and field population. And the difference is that the velocity dispersion that we obtain for quintuplet cluster in our data is unfortunately bigger than the velocity dispersion of other works. And this is due to the high uncertainty of our proper motions that we obtain. And why is that? Why do we obtain high uncertainties for the proper motion? This is due to the fact that the NICMOS detector has a small field of view. So when we want to align it with Hawkeye, we have the problem. And also the signal-to-noise ratio of HST Passion alpha images is not comparable to Galactic Nucleus signal-to-noise ratio. But at the end, by doing some significant analysis and to just get the significant values, we can have the significant proper motion that are plotted here in this figure on top of a Hawkeye image. So this is back to our analysis field 19 chip 1, because we realize, okay, our measurement is fine, we use quintuplet cluster, we realize, okay, we can continue working on proper motion analysis. So when we look at this image, we could see for the first time a group of co-moving stars that are located in this blue circle and are coincident with the H1, H2 region that are moving in the same direction. So we thought that this is very interesting to be studied further, and because it could show a remnant, this star could be a remnant of a young star cluster. So here is the same vector point diagram that I showed you before for quintuplet cluster, but this time is for field 19 chip 1. You see the co-moving group of stars where they are located in this plot. They don't clump together like they clumped and they shape a cluster in quintuplet cluster, but they occupy similarly narrow space than quintuplet cluster. But we wanted to do further analysis to see if these stars are GC stars, if this co-moving group of stars are located in the GC, or are they foreground stars. So what we did, we used color magnitude diagrams. Here you can see K versus H minus K. These two stars that are located below H minus K value of 1.3 are foreground stars. But the stars that are on the right-hand side are GC stars. There are two stars here that have the H minus K value more than 2, are located here. These are the reddened cluster members. But the stars in the middle that you see here, between 1.3 H minus K and 2, these are the sources that we can say they are consistent with being main sequence or post-main sequence star with the age of a few to a few tens of mega year. But we analyzed this further because we wanted to see if we can really say something for the ages of these stars and also the metallicity of them. So we used Basti model to simulate the stellar population with getting solar metallicity stars, and we obtain the isochrones for these stars. But the problem is that we obtain two different ages for these stars, and this was expected because the number of the stars of our study is not much. This co-moving group of stars that are shown here with these red stars are not much, so they cannot, we have a lot of bias and we have a lot of degeneracy, so we cannot, based on this model, obtain the age. And also we have a lot of extinction. The field is quite complex and the extinction can change in the order of milliarc second, and that's why we have quite degeneracy here. But what we did is, in order to make sure that this group of stars that we discover is really cluster or not, because the number of them is not much, we did an analysis with Monte Carlo simulation, and we defined two parameters. One of them velocity compactness, the other one position closeness. What does it mean? It means that how much stars are close or how compact are stars in velocity space and position space. So it shows the compactness. But for us, it's important to check this to say if it is a cluster or not. And the dashed lines here are these parameters for the observed cluster. But the distribution that you see here is from the simulated stars, group of stars that are compact stars from the Monte Carlo simulation. And we see the observed values for our cluster is around 3 sigma and 7 sigma from the mean value of the random distribution. So that's why we can say the group of stars is a real group of stars, and we can say that it is related to a dissolving young cluster. This is a summary of the pilot study that so far we did. We use HST Passion Alpha, we use Galactic Nucleus, we have two different epoch, 7 years baseline between them, we calculate proper motions. And we obtained the first group of co-moving stars, which is at the position of H1, H2 region, which is a supposedly young stellar region. And we could measure proper motions with an accuracy of 1 milliarc second per year. And we did several significant analyses, and we could say that this is shown as a dissolving young cluster at the GC. So far we had 3, Arches cluster, quintuplet, and nucleus star cluster. So this could be one cluster that is dissolving and is losing its stars. So what we are doing now is further analysis of proper motions of these two epochs that we have, but for the whole region of Galactic Nucleus and Passion Alpha survey. So we have a lot of fields, a lot of chips, and we have to go through them one by one to obtain the proper motion and to see if we can whether find more of these young clusters or not. And if we could find more of these clusters, this would be very interesting for the follow-up observations at VLT and at ALT. One can propose to observe these young clusters. So, as I said, proper motions so far have been done on these small regions, Arches clusters, quintuplet cluster, and nuclear cluster in the whole region of GC. These were the only places that people studied proper motion. But what we want to do now is to study all these regions that you see with white squares. We want to study all these regions and obtain the proper motions of them. So the region is 1,000 times larger than any previous study done. And we have proposed to use Hawkeye again to have the second epoch for the Galactic Nucleus. Because we have one epoch till now, we want to have the second epoch. And this will help us a lot because we can get rid of the difficulty of HST Nucleus, and we can trust more on the analysis that we do, and we don't need to deal with all the problems of alignment and uncertainties. And this is the program that we propose, all the regions that are shown here, to be observed this year. So we have got time, 30 hours of observation, to observe in H-band all these regions. And this time Hawkeye is upgraded with Graal, so the quality of the data would be even better than the Galactic Nucleus. And Graal is a ground layer adaptive optics system which is equipped with lasers. And it could have a stabilized PSF, and we can have longer exposure times. And this time we can use the entire field of view of Hawkeye. We don't need to divide it to a smaller fields that we did for using speckle holography before for the Galactic Nucleus. So this means that our observation would be very efficient, much more efficient than Galactic Nucleus. And we can use thousands of stars to align the images of Galactic Nucleus from one epoch to another. And then later, when we measure proper motions, we are going to transfer them to Gaia reference frame, because this is our goal, to have also the absolute proper motions for the whole region of Galactic Centre. And if we use Hawkeye and Graal together, we hope to reach 0.5 milliarc per year accuracy for our proper motions. And we will have much more stars by aligning these two epochs, around 100 times more stars. And so the goal to observe with Hawkeye Graal in future, or this year that we will observe basically, is to discover different things. One of them is to discover young stellar clusters, these clusters that I told you are interesting for our study. The other thing is to disentangle different overlapping galactic structures and populations, and we can, for instance, disentangle galactic disk and bar from nuclear stellar cluster and nuclear stellar disk. We can provide a catalog of proper motion for the community of Galactic Centre. And this catalog can be used for the follow-up observation with imaging and spectroscopy to improve stellar evolutionary models, to be used for chemical evolutions, and also to have a conclusion on recent star formation at the GC, and also to basically constrain the initial mass function for the Galactic Centre. Another observation that we are going to do this year is a spectroscopy with CMOS. So we were interested to see what is the nature of the co-moving stars that we discovered. And for this reason, it's nice to have the spectrum of these sources. We want to use CMOS, which is a K-band multi-object spectrograph. It has an integral field spectroscopy in near infrared. And it has 24 arms that you can see here, the distribution of these different 24 arms. And also it has 24 IFUs. And we can, at the same time, have 24 spectrum of the region of our study. So here you see the setup of our observation. We have been granted to observe these sources with CMOS, and you see here the red crosses are the position of the co-moving group of stars, and we have our observation in the mosaic mode. This region here is the mosaic mode of CMOS, and all these circles here are the position of the arms, of the 24 arms that are located in different position of this square. And also by using CMOS, not only we can obtain the spectrum of these sources, we can also obtain the spectrum of the sources close to these co-moving stars. And this is important because for some of these stars, we couldn't obtain the proper motions due to the limitation of our analysis. But if we have the spectrum close to these stars, then maybe we can say something better for the, or something more conclusive for the young stellar cluster that we detected. And also the observation is in K-band. So what can we say is to detect, to conclude if the stars are young stars and hot, or cool stars. If they are hot and young, they have a featureless continuum, but they can have bracket gamma absorption line. And if they are cool stars, we can have CO absorption lines in their spectrum. So by this, we can say if our stars are young or old when we observe them. And yes, and the image that I show here, the background image is the image of Hawkeye in K-band. Is nothing related to CMOS. So yes, thank you very much.
So it's time for question now. Any questions?
Do you have any information about the radial velocities of these stars?
We don't have, and that's why we would like to have the spectroscopy, basically, information of them.
Okay. In this case, with only proper motions, do you think that you can determine the rotation curve of this population, for example?
For back to your question, for the radial velocity, for instance, that why we cannot have it for the galactic center, the problem is that it's so big and we cannot use, for instance, a slit spectroscopy or integral field spectroscopy to observe the spectrum of all these stars. And it's just so much, is very expensive, first of all, to do the spectroscopy of all. It has been done for a small fields of views, but not for the whole region. And it is actually very interesting. It is a topic that it is under discussion, that one can have because right now we have the proper motion. So if we have the other motion, which is the radial velocity, then we can have the orbit of these stars. And this would be very interesting. But it is still under progress to see what to do for getting the radial velocities.
If you can't, because you know, most of the mass is not made of these giant or supergiant stars that you see in the image. Most of the mass is from dwarf stars that are not visible. But they are those that contribute the most for the mass of this part of the galaxy. I wonder whether this very inner bulge, it follows the same rotation curve as the whole bulge. I mean, it rotates like a solid body, for example. In this case, if you could determine the rotation curve, it would help to answer this question.
Motion, I can say something that yes, because different structures, different places have different proper motions. So for instance, when you are in the nuclear stellar disk, the proper motion is different when you are perpendicular to the direction of galactic plane. And also the proper motion inside the clusters is different from the other regions. So by this, one can say, one can disentangle these different components. But more than this, yes, for instance, there are surveys like Apogee that they have a spectrum of all stars, but they are not for all the stars. They are for some regions. It's not available so far to have a catalog. It would be very nice to have. Yeah.
And so the nuclear bulge has a disk-like rotation from apogee. A disk-like rotation from apogee, but it's decoupled from the bulge itself. But yeah, I mean, it's from old maser work. It's known that it's rotating the nuclear bulge, and it's also known from apogee. But as Banafsheh said, the number of stars that one can measure spectroscopy of is absolutely minor compared to what we can do. We can do proper motions maybe for 1 million stars, and radial velocities maybe for 1,000 stars. So it's a factor 1,000 different.
Thank you very much, Banafsheh, for such a nice talk. I have two questions that come mainly from my ignorance on the field. So first one is, you've said that you have two images and two epochs, so you calculate, I guess, the velocity, I mean the shifts in, let's say, X and Y, and then from that, how do you calculate kinematically to which component they belong, to disk or bulge or bar? How do you translate that information?
I have in the normal image, for instance, I have X direction and Y direction. And I know the direction of the image, where is north and where is east. And I can say which one is perpendicular to the direction of the galactic plane and which direction is parallel to the galactic plane. This is because, for instance, in this image, I can show.
Yeah, but how do you estimate from those values, the X and Y I see, but from the values that you get, how do you know which star belong to which component, to the disk or the bulge or the bar? How do you make that translation?
Right now, I cannot say with my analysis, with this pilot study that I did, is for a very small region, and I could just resolve a young cluster. But in future, that we have the proper motion of all the stars, then one can say that if it is like parallel to the direction of galactic plane or perpendicular to it, then one can disentangle, and then one can say, okay, this is for this distribution, this is for this. Right now, I cannot do that. But later, after I have more data, then I can say that. But the velocities is like what you say, from the difference of the position. But like here you see in, for instance, X and Y direction is like this is north, this is east, and we have the galactic plane, and it is either it is Vx, which is parallel to the galactic plane, or Vy, which is perpendicular to the direction of galactic plane. So by this, one can say that because when you map this proper motion on top of your astronomical image, you can see the direction of them, and you can see the quantity of them, and you can see where they are located, and then you will see that what is the value for the stars parallel, moving parallel to the galactic plane, or perpendicular to it. Like you can disentangle the...
Okay, that's a good...
One cannot do... After you have the survey of the whole proper motion, then one can look to say... Yeah.
Okay, yeah. It's impossible. Okay. And so the second question is, when you've shown the spectra that you're planning to get with CMOS, in your fiber, I guess it's a fiber or something like that.
It's an IFU, not a fiber. It's mirrors. It's a mirror slice.
Okay, so in the size cover, but you, dispersing whatever, you have more than one star. So you will have the integrated spectrum. So how do you deal with that? Because you're planning to analyze the type of each one of these stars, but you have integrated spectra, right?
And I will have the spectrum for each position of this star, so I can have the spectrum for my co-moving sources, right? If this is your question.
IFUs, you get 3 by 3 arcsecond image for each arm.
Say that integral field spectroscopy, right? That you have X and Y, and for each position of the image, you have the wavelengths. So when I have the
resolution of that you have, because otherwise you will have many stars in your resolution unit, right?
I don't know. I'm not sure about the special resolution of CMOS. I'm not sure about. Yeah.
So it's right, but there will be always a dominant bright source, and you can.
You take the brightest there, okay.
Don't have a very, very bright source, so we are confident that we can resolve this star. And actually the detection limit of CMOS in K-band is around 14.5 magnitude, and the sources that we have are detectable, are like, I don't know.
You're pointing to, I mean, the brightest is bright enough not to be, not to need any kind of population synthesis, decomposition or whatever. You just so
not too faint that we cannot resolve it with CMOS, and it's not too bright that we have a saturation. Yes.
Thank you. I would like to ask about this speckle interferometry you were talking about. So that was just basically because of the atmospheric things, or you did it because of something related to the
higher angular resolution for the yes
nation practically, and that cannot be used for the IFU units. Not at all. Never. Like 2 meters, lots of short.
With short exposures. Even it cannot be used for the VVV survey that I showed, because VVV survey doesn't have short exposure time. For this galactic nucleus, Rainer as a PI asked for short exposures, but very fast. And this is what is needed for doing a speckle holography technique. And that's why it cannot be used on VVV. Otherwise, it would have been nice to have higher angular resolution for this survey as well. Yes.
And you can beat the Nyquist limit. So if the pixel scale of CMOS, I think, is 0.2 arcsecond per pixel, something like that, and Hawkeye it's 0.1, but for example, VVV has a 0.34 arcsecond per pixel scale, so you will never get better than 0.7 arcseconds by definition. So you cannot beat the Nyquist sampling.
There are image processing techniques, super resolution techniques who are trying to go under the pixels and
yes, but again, then you need a huge amount of data of short exposures. That is true. We have kind of, we can do this also in our speckle data. We go a bit better than the Nyquist, but you really need a huge amount of data to do that. Yeah.
I have a question and a comment. The question is, well, you have some of the fields are much denser than others, and you talked about Gaia for reference frame matching, but maybe for some of those not so dense regions, can you use solutions from Gaia astrometry to incorporate to your feed to the proper motion? Because also with 2 points or with 3 points in the future, proper motions are more limited because the longer the time span and the number of points is better. So do you think it's possible to incorporate that as Gaia solutions to your measurements?
Yes, but for the very dense regions, actually we thought of doing something. We didn't use Gaia. But what we thought is because we had this problem of very dense regions and it's not homogeneous, so when you want to calculate proper motion, you have difficulty. So what we did is that to make a grid of all the stars of each image that we want to align with the other epoch. So, and in this grid, each star is considered if it has a minimum value of uncertainty among the stars around this source. And this is how we could resolve the problem of very dense region, and we had less uncertainties. But we didn't incorporate yet our data with Gaia. Our hope is to get the new data with Hawkeye, Graal, and then we can have more accurate proper motion, and then later to tie our proper motion into the Gaia reference frame. But for now, because when we wanted to align the images, first we have to select some reference stars in order to align. And for that, we thought the total relative proper motion of one field should be 0. And that's why we trusted to select randomly some stars in order to transfer them to the another epoch. And that's why we thought it is robust, and we didn't use Gaia.
I think you two are talking a bit also. Tell Javier what the extinction in the optical to the galactic center is. I think he thinks about using Gaia, and you think about, we think about using Gaia to get into the frame of the galaxy, and I think you think about actually using Gaia to in the galactic center, right?
Yeah, to measure proper motions with.
No, but it's blind. Gaia is completely blind in the galactic center. It cannot see further than 3 kiloparsecs in the galactic disk. We had 8 kiloparsecs and 30 magnitudes of visual extinctions. So Gaia is completely useless in the galactic center.
Okay. And the quick comment I wanted to do, you are going now in the regime of sub-millisecond second, which is quite amazing. So maybe for the future, a challenge for the future is to start thinking about parallax measurements. I mean, it would be very impressive to be able to measure accurate distances beyond and in front of the galactic center. But I think, well, it's still too early. I think you need much better accuracy, but I think it's a first step in the good direction at least.
Okay. Yeah.
Very quick question. All the stars that you analyze to determine proper motion are punctual or punctual sources, or it can be punctual sources, or it can be extended point sources. Point sources, yes. Okay, because to determine proper motion for extended sources could be difficult because they can change the morphology from one epoch to the other. I was thinking about the H2 region that you had mentioned. I don't know if for them you had inferred proper motions.
Are not really in the bow-shock shape of this H2 region, you know. It's not really inside this H2 region, but it is coincidence around it, the stars that I have. Yes, but if it is in a position that has gas or something going on, then yes, it's more tricky to get a absolute position and proper motion. It's more difficult, but for this, it was not really on top of this gas. Yes.
Okay. No further question, then let's thank Banafsheh again.